Hello guys, this is Dr. Jan Knows Chemistry. Welcome to the channel. And if you are also one of the students that you have issues understanding electrons and orbitals, like majority of the students do, all right, don't worry. This class I'm going to do just that. And in a couple of minutes now, I'm going to jump straight into it, all right? We'll be discussing how we fill electrons into orbitals and some principles that guide doing this, all right? A lot of you already know exactly what I want to discuss because it gives you a lot of issues, all right? So filling electrons into orbitals, we're going to be discussing three different principles. First one is Albau principle, all right? All right, the second one is Hund's rule. Hund's rule. Sometimes we say of maximum multiplicity. And the last one is Pauli exclusion principle. All right. These are the basic rules that we use to describe filling electrons into orbitals. But I'm going to be doing lots of things here because if you find it difficult writing electronic configuration properly, especially maybe of the first 30 elements from hydrogen to zinc, all right, then you have issues with all of these. All right, so we want to quickly start from Albau principle. All right, so let's quickly get into it. Albau principle. All right. Okay, so what does it actually talk about? It says that when filling electrons into orbitals, we fill in ascending order of energy level. Okay, that means we fill the lower energy first before the higher ones. All right, imagine you're just filling electrons into, you're filling water into a tank. All right, let's say this is a tank of water. If you puncture this tank at this point and pump water through, water comes down first before it goes up. Irrespective of where you puncture the tank, the water flows down, then rises up. All right, that's similar to what we have Albau principle. We fill electrons first, all right, from the lower energy before the higher ones. Let's see how to build up this Albau principle. Let me just start by saying, let's say 5s, right? You can do it with me, 4s, 3s, 2s, and 1s. These are s orbitals. 1s, 2s, 3s, 4s. After s, we have p. Let's say 5p, 4p, 3p, and 2p. We don't have 1p. When we get to Pauli exclusion principle, I'm going to be explaining this exactly why we don't have 1p. All right, so after that, after p, we have d. Let's say 5d, 4d, and 3d. For the same reason, we don't have 2d. Don't worry. When we get to Pauli exclusion principle, we'll sort that. After d is f, 5f, 4f. We don't have 3f. Now, these are the orbitals, okay, or subshells. So if you want to fill electrons into this, we fill this 1s first. Then after that, we fill 2x. Can you see that? We fill 2p and 3s. Then 3p, then 4s, then 3d. I won't continue from there. Let me just write what I've just done. We fill 1s first, then 2s, then 2p, then 3s, 3p, and then 4s, then 3d. All right, what it means is this 1s orbitals, is of lower energy than this. So that means this is the lowest energy. All right. Remember, 1s is closest to the nucleus. It's the first shell closer to the nucleus. So the electrons there, they're having a form of attraction with the nucleus. Nucleus is possibly charged because nucleus has proton and neutrons. Neutron is not charged, but proton is possibly charged. So the electrons closest, they are in the 1s. So they're going to be interacting with this proton. So they don't have enough energy. And the electrons go there first before the higher one. So from here now, this 5f is the highest energy level from this direction. If you have 6f, it's still higher. So when filling electrons, we fill 1s first, and we have to fill it before the electron overfill from this and jump into this. All right, then P, then this, then that. All right. So like we have said, s orbital, the maximum number of electrons we can fill it is just 2, because it's just an orbital that is there, a box. So 2 electrons can fill it. All right, the same thing with 2s. All right, so if I put 2 here, 2 here, let's look at p. P has 3 degenerate orbitals. Can you see? That's why we split it like this. So each orbital is like this box. Just think of it as this box. All right, that is the orbital. All right, 2 electrons each. The maximum of electrons that can occupy an orbital is actually 2. So 2 times 3, that is 6. That's why it's 6. Let's go to D, because we're going to be ending with D, because for your exam we're interested in the first 30 elements. All right, D is 10 because it has 5 degenerate orbitals, and I told you that orbitals are just each box like that with 2 electrons in each of the orbitals, so that makes it 10. All right, so if you look at that, so if I put 6 here, 2 here, 6 here, 2 here, in the order of the energy level, the lowest energy being the 1s, because it's the orbital that is close to the nucleus. All right, if I want to tell you what is really this orbital, all right, the orbital is not something that you can just say, oh, this is where it is. All right, it's a big complex. For example, if you say we are looking for somebody in the world, and everybody say, where is this person? And someone say, oh, this particular criminal that we're looking for is somewhere in the world. Of course, you will know that's not information enough, because where do you exactly want to go to know that you'll be able to locate that particular person? So if somebody gives information that that person is in Nigeria and is in Lagos, is somewhere, of course, that is a very direct information. So the region of space around the nucleus where there is maximum probability of locating an electron is what we call orbitals, and they have their different shapes. All right, S, P, D, and all that. So the maximum possibility of locating an electron, and that is what we call orbitals. All right, so just take note of that oh, we don't know exactly where electron is located, we're looking for it. All right, but that maximum, that region of space where there is maximum probability of locating the electron is what we call the orbital. So some orbitals now look like, oh, let's map out this area. All right, this area, this guy is likely going to be here. So that is spherical, and that is how S orbital looks like. Are you getting what I'm saying? So that is how S orbital looks like. So S orbital is what? Is spherical, okay? Is a sphere, all right? Okay, so P orbitals, it looks like this. That's the region. That is the trace of how the P electrons in the P orbital, that's how they move. So this one can be in Y direction, X direction, or even Z direction. Okay, look at that. It can be X, Y, Z plane, and that is what we have there: Px, Py, and Pz. So that is why this is actually called subshell, P subshell. Why this Px is the real orbital, Px orbital, Py, and Pz orbital. All right, so 2 electrons can only be in P orbitals. All right, so D is double dumbbell. All right, in advanced chemistry later we're going to be talking about just very complex. That's 5 degenerate orbitals, all those ds squares and all that. So but let's quickly see how we are filling electrons for this. So that leads us to electronic configuration. How are these electrons configured? How are they arranged in different atoms? And that is what I want to quickly do before we now apply on through and see Pauli exclusion principle. So if you have issues with orbitals, Haber principle, Hons-rule, Pauli exclusion principle, just relax. Let's take it one after the other. All right, now we want to write the electronic configuration of the possibly first 20 elements. We're going to be skipping some elements. I'll just give you and you will tell me. All right, look at hydrogen is number 1, has just 1 electron. That shows that we are filling 1s first. So 1s, 1, right? So this is the electron, okay? So that is it, electron in the s orbital. That's just what it means. This one means that it's in the first shell. All right, so it means that the first shell, that is the K shell, then the s orbital, and we have only 1 electron there. Okay, so that's what it means. So that's why the electronic configuration for hydrogen is 1s1. Let's go to sodium, that is 11. All right, so we are filling 1s first. So 1s, then followed by 2s. Can you see that? Then followed by 2p. Okay, so then followed by 3s. So 1s2, because we have 11 electrons, 2s2, we have, then this is 2p6, that is like 2,8, making 10, it remains 1, 3s1. So this is the electronic configuration for sodium, because if you find it very difficult to write, then it's going to be very, not very easy for you to deal with some of these principles that we use in feeding electrons into orbitals. All right, let's see for calcium. All right, calcium is number 20. All right, so calcium is number 20 now. So what is the electronic configuration for that? So 1s, you fill it first, 2s, 2p, 3s. Look at that, that's what is it? 3p and 4s. Let's see whether this can take the 20. So this is 2, 2, 6, 2, 6, and 2. If you add everything together, that is 20. So that means calcium actually has 1s2, 2s2, 2 pieces, 3s2, 3 pieces, and 4s2. All right, so that is what we have to understand. All right, so 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. All right, now look at that. We have this electronic configuration. This is what we call orbital electronic configuration. Of course, we also have another way of writing, which is called shell notation. And I want to bring the two together so that you have the full understanding of what we are talking about when it comes to writing electronic configuration. This is the same thing as the K element form, which is the shell notation. All right, let me show you what it is. All right, let me even just do that. Sometimes a student was asking me the other time, I mean some years back, saying that, oh, why are we filling calcium to be 2882? All right, when the third shell, we can have up to 18 electrons there. All right, let me tell you something before we go forward on this Albert principle. The student asked me, why do we fill calcium to be 2882? All right, when we have third electron being occupied by 18 electrons. Maybe in case you have forgotten, it's better for me to quickly delve into that so we could quickly move forward from there. Now, what is the number or the formula used to calculate the maximum number of electrons that occupy maximum number of electrons that can be accommodated in a particular shell? And that is 2n squared. All right, so we have K, L, M, N. All right, let's follow this story because it's very, very interesting. Some of you have a little issue concerning this without knowing. All right, so of course K is the first shell, L is the second shell, this is the third shell, and this is the fourth shell. So we'll put N there. All right, don't mind me, that is N. Okay, so now what is the maximum of electrons that can occupy K shell? What's the maximum of electrons that can occupy K shell? All right, so that is, we use the formula 2n squared for the one that can occupy this one too. All right, so K shell, this is the first shell, is 2n squared. That is 2, 1 squared. That is 2. That shows that the maximum of electrons that can occupy the first shell of an element is 2n squared, which is 2. All right, for the second one, second shell, which is L shell, so that is 2, 2 squared, which is 2 times 2 times 2, that is 8. All right, let's go to the third shell. So that is 2, 3 squared. All right, so that is 2 times 9, which is 18. And then the fourth shell is 2 into 4 squared, which is 2 times 16, which is 32. All right, so the student was asking me, why do we write the calcium, which is 20, as 2882 instead of 2810? Have you ever observed that too? all right, because this particular question troubles a lot of people, all right. Why not 2A10? Because the third shell can actually occupy up to 18 electrons, all right. How come when we have not completed the third shell, we go to 8, then we jump to fourth shell? And that is actually what this electronic configuration in Albert principle can help you solve out. In case you don't understand, what is the K element form? What is the shell notation for calcium? All right, that is, why is it not 2A10? Okay, why is it not 2A10? Why is it 2A2? All right, so that is the question that Albert principle can help us sort out. All right, we can easily sort this one out in one of the ways we are filling electrons into orbitals. If you want to know that you really have issues, maybe you don't know, I can give you another question so that you will see, you will be in the right perspective while we are working out using this Albert principle. If I tell you after calcium, the next element is scandium, which is number 21, how would you write the electronic configuration in K form? All right, just think about it. You can pause, maybe at the end of this class you'll be able to quickly do that. All right, majority of you don't know that. You can even be asked, what is the shell notation for there's the electronic configuration in shell notation, that is K element from 2881 to for scandium. So are you saying that you will not be able to write it? Of course, a lot of people make a lot of mistakes from there. So let's see how we can relate this shell with orbital electronic configuration. Those are the two ways of writing electronic configuration of the elements. And we have said that the Albert principle state will first of all fill the lower one before the higher one. And what's the implication of this? All right, and that is what we want to possibly treat now. All right, now we are using Albert principle to write orbital electronic configuration. That is settled. We are filling the 1s first before anything else. All right, so let's write for calcium now. Calcium is 20, which is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. All right, what it means is this number you are seeing here, which is the coefficient of this subshell, it represents the energy levels in an atom. Energy level in an atom. That shows that this is the fourth shell. In the fourth shell, we have s orbital, and there are 2 electrons in it. Let's see whether you can interpret the second one. 2s2 means that in the second orbital, we have s and p orbitals. 2 electrons are in the s orbital, while 6 electrons are in the p orbitals. That's what it means. In this one, third shell, we have 2 electrons in the s orbitals and 6 electrons in the p orbitals. Then the fourth shell, so let's write now, fourth shell, that is 2 electrons. Can you see that for calcium? Then second shell, 2 plus 6, making 8 electrons. So shell notation does not show which orbital we have or which subshell we have electrons. Can you see? That is 2, 8. The third one, 3, okay? So as 6 and 2, that is another 8. 1, 2, 3, 4, 5, 6, 7, 8. Then the last one, which is 2, has that 2 electrons. Can you see that? So that is why calcium is 2 in the first shell, that is K shell. Then 8 in the second shell, 2, 8. Then the third shell, that is 8. Then the fourth shell, that is 2. So that is why it is 2, 8, 2. All right, so let's go to scandium. All right, which is 21. If I want to write scandium, I will first of all get to calcium, which is 20. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. After 4s2, what's the next one? Based on what we wrote before, that is 3d1. All right, that is 3d1. So you can see that first shell has 2 electrons, so that is 2. Second shell has 8 electrons, that is 8. Third shell Can you see that? Third shell has 9 electrons, while fourth shell has 2 electrons. Can you believe that 2892 is the shell notation in K element form electronic configuration for scandium? So you can see now that electron will continue to go into this third shell. The reason why calcium is actually 2882 is because there is no d orbitals for the first 20 elements, which you can see. All right, and there is this kind of energy overlap between 3d and 4s orbital, and that's where there is issue, and most people don't know what it is. All right, so once in the absence of 3d, the last shell, the last energy level after 3p is 4s. All right, so that is why the electron go into it. Okay, that is why the electrons go into it. Why, when the electron now comes into the 3d orbitals, then it becomes a bit lower than 4s. So there is this energy overlap between 4s and 3d, and that is why you see this. You can see that the third shell can actually occupy more than what is it called, 8 electrons, as you have been seeing as 3. It's not because we have used this formula to show that the third shell can actually accommodate 18. Let me give you one example so that you can see. Zinc is number 30. All right, zinc is 1s2. Look at that, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10. If you add everything together, it's going to be 30. All right, so the fourth shell has 2 electrons, the second shell has 8 electrons, the second shell has 8 electrons, the third, can you see, 2 plus 6 plus 10, that is 18 electrons, while the fourth shell has 2 electrons. Can you see, 2, 8, 18, 2. So we can see that there is a kind of relationship between orbital electronic configuration and this shell notation. So it is not the maximum number of electrons that can occupy this 8 shell is not 8. It is by what it is, which is by using this 2n square formula. Is when you write the electronic configuration, you now be able to use orbital electronic configuration to see which shell. When you say 2s2, it means 2s2 means that the energy level is L because it's KLMN. So is the L shell, second shell, first shell, second shell. The s orbital in the second shell, that's where the electron is. Okay, so you just use this one to be able to know how to work out the electrons, number of electrons in each shell. So the third shell can actually accommodate more than 8, and at the same time the fourth shell can accommodate more than 32. All right, I just want you to see how we can use Albert principle by filling up the orbital configuration and use it to interpret into shell notation. How you understood this? This is a very, very important concept in chemistry that most people miss. All right, and they don't understand how these orbitals are forming. Okay, so I think that is what you need to know for now about Albert principle. Just to let you know again, is when filling electrons into orbitals, we fill the lower energy first before the higher one, and that will lead us to the second one, which is Hund's rule. All right, Hund's rule. Let's quickly treat Hund's rule and see how we're going to apply to using how to understand more about the filling of electrons into orbitals. All right, that is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. All right, Hund's rule. Now, how does this this particular rule come about, and what is this rule trying to tell us about the electrons and orbitals? Now, Hund's rule says that when feeding electrons into degenerate orbitals, I have to state that again. When filling electrons into degenerate orbitals. So you may want to ask me, degenerate orbitals. What are degenerate orbitals? It means orbitals of the same energy level. Okay, orbitals of the same energy level. All right, so when filling electrons into orbitals of the same energy level, we fill singly first before pairing takes place. We fill singly first before pairing takes place. All right, so we fill singly first before we pair them up, and let's see exactly how we're going to do that. All right, and I want you to pay attention. If you are feeding electron into orbitals, we fill it singly first before pairing takes place, and that has to do with degenerate orbitals. That means alpha principle may not be obtained in s orbitals because it's only just one orbital. Let me show you what I mean. Let's write, for example, the electron configuration for oxygen, which is 8. Oxygen is 1s2, 2s2, and 2p4. That is, the first electron has 2, the second electron has 6. That is 2, 6. All right. So the 1s2, that is the lowest energy. You feel electrons here. All right. That is 1s2. Then 2s2 is still one fold. Can you see? Feel electrons there. That is 2s2. Then the last one, this is where the Horn's rule is working. All right, look at this. 1s2, 2s2. This is the degenerate orbitals we are talking about, p4. All right, the degenerate orbital in the sense that you can see that there are triplets, 3 orbitals. All right, and they have the same energy level. So this is where we can apply Horn's rule. Horn's rule states that when filling electrons into degenerate orbitals, we fill singly first before pairing takes place. And let's see how we're going to fill that. All right. Some people may say, well, like, because we have P4, so 2 and 2. Can you see that? Just like you have triplets, 3 children, all right, and you want to give them 4 million now. You have 4 million. I give the first child 2 million, the second child 2 million, and nothing here. Of course, that's not going to work. That will create chaos in the house. All right. So if you want to restore stability or order in that house, you have to collect back the money. And because you have 4 million, you can say the first child take 1 million, the second take 1 million, the third take 1 million. Of course, if you now give this guy second million, they know that their turn is coming, that you don't have up to 6 million. That's why you have this. All right. So what it means is, like, first of all, I fill it singly first before I now pair it up. All right. So this is the pairing. So you can see now that instead of me to just write 2, 2 here and nothing here, so that is like not going to happen because the electronic structure will not be stable. All right. There will not be order there. All right. There will be cheating. All right. So this is what Horn's rule is. When filling electrons into these degenerate orbitals, all right, we fill it singly first before pairing takes place. All right, and this particular rule, we can use it to identify or to calculate the number of unpaired electrons, because we fill it singly first, that is unpaired, before we pair it. So after pairing, how many electrons still remain single? All right, how many don't still have partners? Okay, so that is, we can use this Horn's rule to calculate the number of what unpaired electrons in an atom. All right, let's quickly get into that and see that. So if I may ask you, I will say, how many unpaired electrons are there in the ground state atom of nitrogen? How many unpaired electrons are there in the ground state atom of nitrogen? Okay, so how many unpaired electrons do we have? How many unpaired electrons are present in the ground state atom of number 1, nitrogen. Number 2, chlorine. Let's just do that and see how we're going to treat that. So how many unpaired electrons do we have in the ground state? Ground state means that it is not charged. That means it's not charged, doesn't have any charge, it has not lost electron. okay, to move to the excited state. All right, so it's just the normal neutral element that has not lost electron. All right, so how many unpaired electrons do you have in this atom? So nitrogen is number 7. All right, so 1s2, 2s2, 2p what? 2p3. All right, so remember I've told you that the last electron here is p, and we can apply the unscrew there. That is 3 regenerate orbitals. If you want to do that, you would have started from 1s2, but it's not compulsory. 2s2, can you see that? So this is 1s2. Now 2p3, you fill singly first. You can't have 3 millions and fill 2 here and 1 here. All right, it's not possible. Look at that. That will make it 3 million, but this one has 2 million, 1 million, and nothing. So it's not going to work. The house will be disordered. Okay, so this is 1 singly. All right, that's 2p3. This is 2p3. All right, so how many unpaired electrons do we have? The answer is 3. Okay, these are 1, 2, 3. This is single, this is single, not paired. So we have 3 unpaired electrons in an atom of nitrogen. Let's see chlorine. Chlorine is number 17. All right, chlorine is number 17, and we're going to write the electronic configuration: 1s2, 2s2, 2p6, 3s2. That is 2,8, 3p5. All right, 3p5. That is it. Okay. We have ended in p orbitals as well, and that is the last place we're going to apply the unscrew. Can you see that? 1, 2, 3. Okay, we have 5 electrons there. That is 1, 2, 3, 4, 5. All right, so we have 1 unpaired electrons. All right, unpaired electrons. So you can see that we can use unscrew to determine the number of unpaired electrons in what? In this chlorine. Number of what? Unpaired electrons in chlorine. That is very simple. All right, so we have just 1 because this is it. That's how to show it. You can't show it from the shell because the shell notation does not even show that electron is in s or p orbitals. Okay, let you know, you will know which one is the degenerate orbital. So it's important for you to know that whenever you want to calculate the number of unpaired electrons, okay, you use unscrew, and unscrew deals with the orbital electronic configuration. All right, and this is what you express. You don't have to write draw the structure like this from 1s, because you keep raising it up till you get to 3p5 and 1, 1, 1, 4 and 5. So we only have this. All right, what about if they are not the elements? Okay, for oxygen we have done it here. All right, how many unpaired electrons? Let's just do that. That is 2. I just saw it. That's the first thing that we did. Example, 2 unpaired electrons in oxygen. I can decide to give you whatever in sulfur. Sulfur is 16. You can just quickly pause the video now and try it. Sulfur is number 16. How many unpaired electrons do we have in the ground state atom of sulfur? All right, pause the video and do it, and later watch. All right, okay, let's do it together. First of all, sulfur is 1s2. All right, sulfur is 1s2, 2s2. We're going to work out let's say number 3, s16. Okay, so let's write the orbital electron. 1s2, 2s2, 2p6, 3s2, 3p. Let's say 286, isn't it? Okay, so that is 286. Okay, so that is still 3p4. All right, 1, 2, 4. You fill it singly first. 1, 2, 3, 4. So that is still 2 unpaired electrons. If we look at sulfur, it has 2 unpaired electrons, and it's the same group as oxygen, 2 unpaired electrons. That tells you something. All right, so it's very easy for you to be able to know how to calculate the number of unpaired electrons using unscrew. But it's not this easy. All right, we are moving gradually to the ones that most students consider very difficult, and that is, how do we use this same unscrew to determine the number of unpaired electrons in the transition metals, 3D elements. All right, those ones, element from scandium to zinc. It's another ball game entirely, because The degenerate orbitals are there. That is D as a degenerate. 5 degenerate orbitals are there, unlike this P that are 3 degenerate. So let's see how we're going to deal with that. First of all, we must be able to write the electronic configuration for the first transition series. All right. Most students find this area very difficult. Oh my God. So, and I want to break it down for you now. Let's see how we're going to do that now. All right. So, I want to quickly write the electronic configuration for the first transition series. That is from 21 to 30. All right. Please, you must note it. If you're writing WAEC, you're writing JAMB, at least you must know the first 30 elements. All right. So let's start from number 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All right. So that is it. That is the atomic number. All right. So the symbol of the element is what I want to write. I only want to write the name so that it won't be. So this is the atomic number. All right. So in the periodic table, number 21 is scandium. All right. Then followed by titanium, okay, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. All right. Because I can do this, so you should be able to do the same thing. So these are the first transition series from 21. Remember, group 1 elements are there, group 2. Between group 2 and group 3, the periodic table looks like this. This is group 1 and group 2. There is a space before you move to group 3, 4, like that. So this space contains 10 elements from scandium to zinc. That's what we're doing. So 21. Calcium is there in period 4, and move like that. So this is scandium, titanium till we get to zinc. All right, these are the first transition series. How do we write their orbital electronic configuration? All right, scandium is number 21. All right, remember we say 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s2. For calcium, 288. Okay, 1s2, 2s2, 2 pieces, 3s2, 3 pieces, and 4s2, 2882. All right. So let's take it like this. That is argon. All right, we can put argon here. That argon represents 1s2, 2s2, 2 pieces, 3s2, 3 pieces. I didn't want to keep writing this, and that's why I represent it as argon. All right. In case you write in the exam, they say write the orbital electron for scandium. Just write the full stuff. This is for calcium, though. We have not added the next orbital, which is another subshell, which is 3D. So this is 18. 4s2, make it calcium. 20. Then after 4s2, we have 3d1. All right. So that is the electronic configuration for scandium. So the real electronic configuration is 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s2, and 3d1. All right. So the next one will be argon. Can you see that? Argon, 4s2, 3d2. All right. The next one will be argon. That is 18, 4s2, 3d what? 3d3. All right. Of course, you want to tell me that this next one will be argon, 4s2, 3d4. All right. Wrong. All right. This last one. Please, let's start that. All right. If you divide them into 2 like that, this one before and this one, copper, they both start with C. Let's just start it so that I can see what I want to do. Now, look at this particular chromium. Chromium just behaves like a normal human being that wants peace in the house. All right. And let me show you why chromium is a very nice guy. All right. So you'll be able to understand its electronic configuration perfectly. Chromium is a very nice guy. And let's see how it goes. All right. Look at chromium. All right. Chromium is 4s2, 3d4. I want to show you something. I said this is wrong because that is what it's supposed to be. But a lot of things that we use to monitor the electrons in an orbital, we find out that the electrons are not arranged in this form in chromium. And I'm going to show you why. All right, this is how it's supposed to be. And this is what the whole world expected chromium to be. But chromium, being a nice guy, says that this is bad. All right, let's see why chromium feels this electron configuration does not belong to him. Remember, it's 24. 18 plus 2, that is 20 plus 4, is still 24. But let's see what it is. All right. Now, argon is like this, which is 18. Now, 4s2 is like this. All right. Then D has 5 orbitals. Are you getting what I'm doing? 1, 2, 3, 4, 5. Or will I make it a bit bigger so that we can see? Because it's a very beautiful concept that you need to see. I really want you to see it. Okay. So I'm doing argon separately. So 4s2. Let me just put like that. 4s2. Can you see? Then D has 5 degenerate orbitals. That's why the maximum number of electrons that can be on D orbital is this option is 10. Okay, so let's do 1, 2, 3, 4, 5. All right. So now Onsu has already told us that when feeding electrons into orbitals, we fill it singly first before pairing takes place. So this is 1, this is 2, this is 3, and this is 4. All right. So each of these boxes, that's what we call orbitals. They are like children to chromium, and chromium has how many children? 1. Okay, let's put it like that. Let's try to demonstrate this so that you can click very well. Okay, because I want to make it click. All right, this is the second one. All right, this is the third one. This is the fourth one. This is the fifth one. All right, there's supposed to be 6 now, because this is the fourth one. These are the 5 degenerate orbitals. All right. Okay, so this is the 6th one. Now, if you have these children in your house and each electron is like 1 million, you give this guy 2 million, give 1, and give this one nothing. How will you solve this problem? All right, is it not very simple? How do you think you want to solve this problem? If this child is crying and he say, "Mom, Dad, you don't like me. How can you give my brothers 1, you gave 1 2 million, you gave others even 1 million, but you didn't give me anything?" You will agree with me that the best thing you can do is like, oh, just tell this guy, come on, just please give me 1 million there. All right, and let's give it to your guy. All right. So there is a promotion of electron from the 4s to 3d, one of the orbitals there. So 4s is now left with 1 and 3d is now 5. Can you see that this configuration is the only solution that can restore peace in this kind of house? And that's what chromium has done. Chromium feels like, why leaving this place vacant when we can promote electron from 4s to d, so making everything to be equal. All right. And besides, these are the degenerate orbitals. They want to tend to be the same, except where it is not possible. All right. For example, if you have 1 more million and you still want to continue to give them as you have it, it's not possible for all of them to be the same. All right. But this arrangement is possible for everybody to be happy. All right. That is why I wanted to write it. This is wrong, but that is 4s1 3d5. So this is the right electronic configuration for what? For chromium. So that's why I said you start it. When this was discovered, we know that, oh, there should be possibility of some other elements behaving like this, caring for the children that they have, and maybe we're going to meet another one. Let's just go on and see. Of course, the next one, there is nothing you can do, all right, but just give this guy back what you collected from him. And that is why it follows another order. So this is what arrangement is called, to restore stability, okay, to make the orbitals to be very stable. And that's why we have that. So for manganese, let's see again, argon, can you see? Then 4s2, we give electron back 3d5. So chromium and manganese, they are 3d5 configuration. If we add it, 20 plus 5, that's 25. Iron again will be argon, 4s2, 3d6. Can you see that? All right, cobalt will be argon, 4s2, 3d7. Can you see that? Nickel will be argon, 4s2, 3d8. Now copper will be argon, 4s2, 3d9. And I say wrong again. Copper now behaves exactly like chromium, and both of them, the name starts with C, although cobalt is also there. And you can see 24, 25, 29, 30. If you divide them into two equal halves, the one before the last, they behave that way. So whenever you're writing the electronic configuration of the first transition series, the first thing you need to do, make sure you start chromium and copper, because they have unusual electronic configuration which does not obey unscrew for stability, all right, of the orbitals. I hope that makes sense. All right, they don't want to obey that because there are better ways of doing it. We don't want to fill this 4s when the d orbital is vacant. All right, so what would this guy do again? This guy says the d orbitals, because they are born the same day, they are just 5. Okay, 1 2 3 4 5. So why will we have 3d9? 1, let me do it singly first. 2 3 4 5 6 7 8 9. All right, when this guy that is separate has 4s2. So what happens just like this one just gives this, you don't feel bad because those are your mates. All right, I will get my own later when it's the first child. So it's just like do the same thing so that there is uniformity and stability here, all right, in this d configuration. And that's why copper did the same thing that chromium did here. So the copper configuration is now 4s1. Can you see 3d10? So this is the right one. All right, why zinc? Just pick it up from there. We have argon 4s2 3d10. Okay, 80 plus 2 plus 10, 30. All right, so these are the electronic configurations, okay, for the first transition series, which you must know. This is how they are. This is what chromium is, and this is what copper is. We don't want to follow Haber principle because we care about our children, all right, and we have to make sure we stabilize our house, the orbitals, in such a way that there will be uniformity. All right, that is stability of the configuration, and that is what chromium and copper, that's what they have done. Now if you now understand this, then you will see that, oh, then it is possible for you now to work out how to use unscrew again to know the number of unpaired electrons in this this particular set of elements. Okay, so let's now do this first. So determine the number of unpaired electrons in the following. We want to unpair the electrons again in the following. Okay, number 1. Okay, we want to determine the unpaired electrons in iron. Okay, ground state atom of iron. Number 2, let me make another one, nickel. Number 3, zinc. Let's just do that like that. Okay, we want to determine the number of unpaired electrons. This one you can be asking your exam. How do we determine the number of unpaired electrons in the ground state atoms? You can say ground state because they are not excited. They have not seen the right atom to donate their electrons to, so they are not excited. So they are in their ground state, all right, by themselves. No charge, neutral atom, all right. So they have not lost electron because they've not seen the worthy partner to donate those electrons for. So it's just iron, nickel, and zinc. So let's see exactly what we're going to do now. How to calculate the unpaired electrons in the ground state atom of these atoms. Okay, so the first thing is iron there. Just understand that iron is number 26, but I've not rubbed it up, so it's argon number 26. Okay, 4s2 3d6. Remember, unscrew is applicable where there is degeneracy, all right, and that is D. You keep drawing 1s2, keep drawing, but we are going to the last one here. All right, so that is d orbitals has 5 degeneracies. 1 2 3 4. We have 5 degenerate orbitals. Sometimes we call it 5-fold system. Okay, so that is it. So 1 2 3 4 5. Now we have d6 because it's iron. Okay, this is configuration. So we fill it singly first before pairing takes place. That is d6. 1 2 3 4 5, then pair 6. All right, so how many unpaired electrons do you have? So the answer is 4. All right, so maybe you should work out this and this. Pause the video now, work out this, and let's see if you'll be able to calculate the number of unpaired electrons in nickel. All right, nickel is number 28. So I can say argon 4s2 3d8. All right, because we are going to d8 configuration, let's see. Did you get this? 1 2 3 4 5. All right, this is 1 2 3 4 5. That is filling singly first. That is 1 through 7 8. So how many unpaired electrons is 2? All right, that makes sense, isn't it? Beautiful. So let's work out for zinc. You can pause the video again and calculate the number of unpaired electrons for this zinc. And let's do that now. All right, zinc is number 30, which is the last of that first transition series. So we have argon, that is 18, 4s2, that's 20, 3d10. All right, that is zinc for you, right? So we are moving to these degenerate orbitals. Split it into 5. Don't wait. It's very easy. 1 2 3 4 5. Very easy. There's nothing complex about this guy. All right, so let's just go. So if you want to fill this, fill it singly first. 1 2 3 4 5 6 7 8 9 10. How many unpaired electrons? 0. All right, but don't forget, those are the ground state atom. Ground state atom, meaning like they are not charged, and that is it. What happens when they are charged? Do you understand that these are metals, and metals are associated with, they are electropositive. That means they want to give out electrons. They don't gain electrons, they give out electrons. So when they find the right partner, species or group to donate electron for, that will make them excited state. They are charged. So after we lose electrons, are we going to lose electrons from D or from S, or how? And that is where I'm going to show you this. All right, let's quickly see this. We are still on Hund's rule. How to apply Hund's rule in calculating the number of unpaired electrons in the excited state of those transition series. But before I do that, let me show you something. For n equals to 1, that is the first shell. All right, so that is the 1s that is there. Can you see? For n equals to 2, that is the second shell. We have 2s and 2p. So let me just put it like this. Okay. So are you watching what I'm doing? I just want to show you something. So 2s and 2p. You can see we fill the lower energy first before the higher one. That's what I'm saying. All right. What about the when n equals to 3? All right. Remember, we have 3 too, isn't it? Or you don't know? We have 3. We have 3s, 3p, and 3d. Okay, when n equals to 4. Okay, so we have what? So this is just what I want to show you. Okay, so I hope you are seeing that now. We have 4s here. We have 4p, 4d, and 4f. Okay, look at that. So I can continue like that, but this is none of our business now, right? This is the first shell. That is what we do like this. This is the second shell. This is the third shell. This is the fourth shell. But look at this. When feeding electrons, we feed electrons lower one first before the higher one. So Albert principle, we're going like that. You can see the reason why we fill the 4s first before 3d. Because 4s is of slightly lower energy. Are you getting me? Let me show you something. For sodium to be, which is 11, for sodium to have this oxygen number of +1 or kind of valency, let's see, which electron has it lost? You will see that it's 281. It has lost the electron in the outermost shell, the highest one. All right? So when you are filling these electrons, you're filling this way. to get to 4s. So 4s and 3s, there is overlap of energy here. Just watch what I'm doing, and you have to get this once and for all. Energy overlap here. All right. See, in the absence of 3D, 4s is the highest here, and that is why we are feeling like this. We get 4s. Can you see 4s is next to 3D? Now, when electrons start occupying the 3D orbitals, that means, you know, 3D is heavy. Put it like that. 5 electrons. When you start putting electrons here, do you know the 3D will now move to this place? That's what we call energy overlap. All right, and the 4s becomes the highest energy, which is far away from the nucleus, and therefore it's not feeling the attraction word, and the electron will be lost first. When 3D is absent, 4s is over here, and that's what I feel. When 3D electrons comes here, energy changes occur, and 3D comes below 4s, and 4s will arbitrarily be the highest energy level where electron will be lost. What am I saying is that whenever we want to lose electron from the excited state of these transition metals, it's very important to know it. We lose electron first from 4s based on what I've explained here. We lose electron first from 4s before what? Before 3D. All right, and let's see how we're going to do that. All right, let's say we are giving Fe2 plus. How many unpaired electrons do we have in Fe2 plus? All right, the first thing you do first, you first do Fe is 26, and that is argon, 4s2, 3d what? 3d6. Can you see? I've not cleaned it actually. So that is ion itself. But if it is Fe2 plus, what it means is it has lost 2 electrons. So you lose electron first from 4s before 3d, because electrons have started coming into D, and S is now a little bit above it, which is farther away from the nucleus. So because we lose electron from the highest orbital first, okay, 4s was highest when 3d was not being filled. When 3d is being filled, 3d goes down, energy overlap, and the 4s arbitrarily higher than it a bit. So we are losing this electron, so it becomes argon, 4s0, 3d6. Can you see that? So we've lost this electron, okay, and 3d6 we have. So we now treat this 1 2 3 4 5. So d6, 1 2 3 4 5 6. So we have 4 unpaired electrons. So let's say number 2 is ion 3. As you know that these transition metals, they have variable oxidation state, all right, and that is ion 3 we have. So how will you do that? You are losing 2 electrons first from 4s. So Fe3 plus will be argon, can you see, 4s0. We have lost these 2 electrons. Then we now lose 1 electron from this, we become 3d5. Can you see that? So because this guy has lost 3 electrons, so this one is 18 plus 5 now, which is 23 instead of 26, because we have lost 3 electrons. I hope you have seen that. So Fe3 plus, which is ion 3 ions, is 3d5 configurations. So 1 2 3 4 5. So it has 5 unpaired electrons. I hope you can see that. Okay, so let's see. If I give you now, let's come to this place. Number 4. What about copper 2 plus? All right, because we have copper 2 plus. All right, copper 2 plus complex are usually blue. All right, so let's see how we're going to determine the number of unpaired electrons in this particular ion. All right, so first of all, you write copper, which is 29, number 29 electron. Argon, remember, copper has 4s1, 3d10. All right, so this is 18 plus 1 plus 10, that is 29. All right, so copper 2 plus, for it to be copper 2 plus, it has lost 2 electrons. So 1, first of all, lose this one and 1 there. So that will make it argon, 4s0 3d9. Can you see that? 4s0 3d9. What does that tell you? So it's a d9 configuration. 1 2 3 4 5. So one electron here, another one, another one, another one. I'm making 5 6 7 8 9. So we have 1 unpaired electrons. I hope you can see that. So this is actually how to calculate the number of unpaired electrons from these transition metal ions. Okay, so let me give you cobalt 3 plus and quickly try it now. Let's try it. Let me give you nickel 2 plus and cobalt 3 plus. Nickel 2 plus and cobalt 3 plus. Okay, let's quickly try that now. Let's try that now so that we can see that. All right, nickel 2 plus, that's number 1. Number 1, manganese 2 plus again, and number 3, cobalt 3 plus. All right, so quickly let's try this together. All right, you can pause the video now and quickly try this. How many unpaired electrons do we have in these transition metal ions? Okay, so let's try it together. Now I believe that you got it. All right, that's beautiful. All right, nickel is number 28 on its own, manganese is 25, cobalt is 27. All right, so I've not even cleaned it, it's still there, can confirm that. So nickel, ordinary nickel atom is 4s2 3d8. okay, so that is 1828. all right, that is it. Okay, but if it is nickel 2 plus, so you are losing these 2 electrons, so that makes it 4s0 and 3d8. You see d8 configuration. So we have 1 2 3 4 5. 1 2 3 4 5 6 7 8. So it remains 2 unpaired electrons. Did you get that? That's beautiful. That's beautiful. So let's see manganese. Manganese is just 25. Okay, so manganese is 25. Okay, which I've written here already. So that is 4s2 3d5, isn't it? That is 4s2 3d5, but it's manganese 2 plus, so we have lost this, so we have d5 remaining. 1 2 3 4 5. So 1 2 3 4 5. That is 5 unpaired electrons. Let's see cobalt, which is number 27. All right, cobalt is 27, so that is argon 4s2 3d7. that is cobalt, but it's now cobalt 3 plus. What it means is it has lost 3 electrons because it's cobalt 3 plus. So we're first of all going to lose this one, 4s0. Remember, argon is here, which is number 18. So we have lost 2. We're going to lose 1 again, 3d6. That shows that cobalt 3 plus is a d6 configuration. So just put it like that. 1 2 3 4 5. 1 2 3 4 5 6. So cobalt 3 plus has 4 unpaired electrons. I hope that is clear. Right, so this is how to use Hund's rule to calculate the number of unpaired electrons in the ground state or excited state. Whether the atom is charged or is not charged, you can just do. But don't forget this switch of the chromium. Why chromium is trying to stabilize the system by making a stable configuration. All right, because of stability and stability, copper and chromium, they don't have the usual electronic configuration. Usual means that they don't follow the Albert principle, because Albert principle, we must fill 4s first before we go into 3D. All right, and look at what is happening. There is promotion of electron from 4s to 3D for stability. All right, that is one thing you have to know about that one. So also remember that when electrons start coming to 3D, they switch the energy changes. All right, between vacant and filled orbitals, energy changes occur. Okay, so that is what causes us to actually lose electron first from 4s before 3D. And I want to believe that this answer is very clear, just like Albert principle. I've been able to discuss Albert principle, being the principle that shows we fill electron first in order of the ascending order of energy level. That means fill the lower energy level first before the higher one, then the Hornstroke, that is fill the degenerate orbital singly first before the pairing takes place. All right, the third one, which is Pauli exclusion principle, and that's what I will be treating in the part 2 of this electron and orbitals. That means Pauli exclusion principle is another one entirely. All right, it's a blend of WAEC, JAMB, and A levels, and that is I will extend it so that when you watch that video, you're going to know everything about Pauli exclusion. It's going to go beyond what you learn somewhere that has to do with just mentioning the orbitals or mentioning the types of different stuff that we have there. We have to study it. What does Pauli exclusion principle say, and how do we break it down at this level of atoms, of electrons and orbitals? So see you next in the next video. All right, and make sure you like and share the video. All right, thank you very much, and I'm going to be meeting you up in the next class. All right, don't forget the next video is going to be on Pauli exclusion principle. Thank you very much, and get yourself past questions and practice all the things you have learned. You see that you now understand it better. Thank you.